Hi everyone, today we're going to look at section 1.7, inverse relations and functions. I know you've had a little bit of exposure to inverse functions, so let's just recall what it means for two relations to be inverses of each other. Inverse relations exist if one relation contains a point b comma a, when the other relation contains a comma b. So there has to be that relationship where the x and y values are switched. Let's take a look at a function and its inverse graphed below. So if you notice, we've got the blue parabola, the equation for which is x squared minus 4. And the green is the inverse of the blue. Its equation is y squared is x plus 4. Now the two are inverses for each other, So let's just explore a couple of the characteristics here. First off, when you look at the relation x squared minus 4, so right here, if we pick some points, some values for x and find their corresponding y values, they're listed in this table. So when x is -3, y is 5, when x is 0, y is -4, and so on. Now, if you look at the inverse relation, where y squared is x plus 4, you'll notice that the coordinate points are switched, whereas in the first case I had -3 comma 5, here I have 5 comma -3. Whereas in the first case we have the coordinate 2 comma 0, here we have 0 comma 2. All right. So another characteristic is the following. Suppose you have a line of reflection. Suppose this red line is a line of reflection. If I were to reflect, so let's just take this right arm of the parabola. If I were to reflect this along the red line, then I would get this upper part of the inverse. And if I now rotated the other part along the same red line, I would get the bottom part. So you can see that the inverse relation is the reflection of the function along the line y equals x, this line right here. Okay? Now, when do we call it an inverse function and when do we call it an inverse relation? All right, so suppose you have a function f. All right, so we know that f is a function. And suppose you were to find its inverse. If the inverse is also a function, then it's called the inverse function. And the symbol for that is f inverse, like this. Now it's important to note that not all functions will have inverse functions. If we look at the example that we were looking for here in the case of the parabola, the inverse, this green, yeah, that's a relation, and yeah, it's an inverse of the blue parabola, but that green is not a function itself, okay? So the green doesn't pass the vertical line test, therefore it's not a function. All right, so how can we figure out from the get-go whether or not a function will have its own inverse function? Well, for that, a function has to pass the horizontal line test. So take a look at this example down here. The horizontal line test is just like the vertical one. And if you draw a series of horizontal lines, each horizontal line is allowed to touch the graph at one distinct point. If that happens, then the graph does have an inverse function, okay? So this means the inverse function f inverse does exist. All right, so let's just take a look at some of these here. It says to graph the function using a graphing calculator and apply the horizontal line test to determine whether the inverse function exists. Okay, so I've graphed the first one here. This is 4x squared. If I trace, you could see up here, it's 4x squared plus 4x plus 1. Now, that's a parabola, and you can clearly see that it's not going to pass the horizontal line test. That means this does not have an inverse function. Okay, now let's do the other one. So the other one is x to the 5 plus x cubed minus 1. And I also have that one here. If I graph it, okay, that's a cubic function. We now know, because we've been talking a lot about this stuff in chapter 2, that that's going to look like this squiggly snake. And it does pass the horizontal line test. So in this case, this does have an inverse function. Okay, so let's move on. What do we mean if what is it called when it passes the horizontal line test? Well, if it does pass the horizontal line test, it's called 1-to-1 because no x value is matched with more than one y value. So that means each of the y values have one corresponding x value. So for example, take a look at this function or this graph right here. Now let's pick y equals 3. If you notice, y equals 3 has two corresponding x values. This is not 1-to-1. However, if you look at this function, now if we pick a y value, you'll notice it only has one corresponding x value. This is 1-to-1. And this is going to have an inverse function. All right, so once we've got a function that's 1-to-1, okay, and if we find the inverse of this function, remember what I said before is the inverse and the relation have their coordinate points switched. A and B becomes B and A. That means the domain of f becomes the range of f inverse, and the range of f becomes the domain of f inverse. So domain and range get to flip-flop. Okay, so if I have f of x and if I have f inverse of x, if this has a domain and range, they switch, and the domain becomes the range of one and the range becomes the domain of the other. All right, now how am I going to find an inverse? Well, first you have to determine whether the function has an inverse. If the equation is written as f of x, we replace f of x with y, and then we interchange x and y. After that, we solve for y, replace y with f inverse, and we should remember to state any restrictions. All right, so let's do this first one. All right, so first it says determine whether the function has an inverse function. So let's see, I happen to have graphed that one as well. So when we go here, this is the third function now. X over 2x minus 1. All right, so here there is a horizontal asymptote, which means they're not nearing the same line. So one of the horizontal lines is above the asymptote, the other one is below the asymptote. So this does pass the horizontal line test. All right, let's find the inverse of this. We're going to rewrite this as y equals x over 2x minus 1. Now, I'm going to interchange x and y. So it's x equals y over 2y minus 1. So just switch all the x's for y's and y's for x's. Now I need to solve for x, solve for y. So let's cross multiply here. So on this side, we're going to get x times 2y, so 2xy minus x is equal to y. Let's collect all the y's to one side. So it's 2xy minus y is equal to x. Factor out a y. 2x minus 1 is equal to x. So what is y then? X over 2x minus 1. So f inverse of x is x over 2x minus 1. Well, what do we notice? We notice that the inverse is the same as the function. And if we go back to the graph, you'll notice that this is its own inverse, right? This one is its own inverse. Sorry. So if I were to take this, and if I would draw the line y equals x, and if I were to reflect it around that, I would just get the same function back. And that's fine. That's okay. So what are the restrictions? X cannot be 1 over 2, right? Because 2x minus 1 cannot be 0 for the denominator. That means 2x cannot be 1, and x cannot be 1/2. All right, so let's do another one. Now this, I don't think I need to graph this one. This is a square root function, and we know that all square root functions will pass the horizontal line test. So we rewrite this as y equals 2 root x minus 1. X equals 2 root y minus 1. Now, I need to square both sides to solve for y. So here I'm going to get x squared is equal to, remember the 2 belongs to both of these, so 2 squared times the square root of y minus 1 squared is y minus 1. So now x squared is equal to, when I distribute, 4y minus 4. So let's see what y is equal to. X squared plus 4 is equal to 4y. So y is equal to x squared plus 4 over 4. All right, that means f inverse is equal to x squared plus 4 over 4. Okay. All right, so now let's take a look at this one. Now it says m of x is equal to x squared if x belongs to the domain of 0 to infinity. So let's take a look at what x squared looks like. X squared looks like this. So clearly it doesn't pass the horizontal line test, but my domain, I have a restricted domain, and it says that it's for all the x's from 0 to infinity. That means everything from 0 to negative infinity is canceled out, so I could just take it out. So that's my function now from 0 to infinity. Now, does that pass the horizontal line test? It does. So it does have an inverse. And let's find what that inverse is. So y is equal to x squared. That means x is equal to y squared. And if I take a square root of both sides, then y is equal to plus or minus root x. However, okay, if the domain of this is 0 to infinity, well, what's the range of f of x? What's the range of this? Again, it goes from 0 to infinity. So these are for m of x, sorry. So for m inverse of x, the domain and range are going to switch, right? They're going to switch. So this is going to become the domain. And yeah, they're all the same. So we're just, swapping around the same exact thing. And the range is going to be 0 to infinity. But the moral of the story is the domain of the inverse is 0 to infinity. And the range of the inverse is 0 to infinity. That means here I can't possibly have this negative one. So m inverse of x is only positive root x. Okay? Another way of thinking is if I only take the positive side of this here, then my inverse can only be the positive here. Okay? All right. Now, you're walking down the street. You see two functions, and the billboard claims that they're inverses. Is there a way to check? There is a way to check algebraically. So the way to check is this. If two functions are inverses, then if you find f of g of x, you should get an answer of x. And if you evaluate g of f of x, you should get an answer of x. Okay, so you do f of g of x, you do g of f of x. In both cases, you need to get x, not any other value that's the same, just x. So in that case, you can say that f and g are inverses. So let's take a look at this one here. Let's see if f and g are inverses. So in the first case, we want to find f of g of x. And then we want to look for g of f of x. So in the first case, this is the square root of. Now g of x is going to go in here. So x squared minus 10x plus 33 minus 8 and plus 5 out here. So let's see. Sometimes this is just magical. So x squared minus 10x plus 25 plus 5. Doesn't look like anything is happening, but let's see. So this is equal to the square root of, if I factor this, it's x minus 5 squared plus 5. Well, what happens to the square and the square root? They magically go away. So I've got x minus 5 plus 5, and finally, f of g of x is just x. Okay, let's do g of f of x. That means I'm going to put f inside of g. Now this is a little bit more work. So it's the square root of x minus 8 plus 5 squared minus 10 times x minus 8 plus 5 plus 33. Okay, now let's square the first parenthesis. You square this one, you get x minus 8. The middle term is plus 2 times 5 times the root. So it's 10 root x minus 8 plus 25. So your knowledge of chapter 2 is coming in handy again. We distribute this, so we get negative 10 root x minus 8 minus 50 plus 33. What a mess. But the 10 and the negative 10 will cancel each other out. And let's see what we've got here. Well, it turns out we've got a 33 minus an 8, which is 25, plus 25 is 50, minus 50, oh my goodness, they all go away, and I'm left with x. So g of f of x is just x. All right, and there you have it. Since I got x here and I got x here, f and g are inverses. All right, last but not least, if you have a graph, how would you use that to graph its inverse? All right, well, pretty straightforward. Remember what we said is that between the graph and its inverse, the coordinate points are switched. So what we do is we pick some representative points. So for example, this one here is negative 3, comma 0. This one here is negative 2, comma negative 1. And I try to pick points that are integer values. This one here is 1 comma negative 2. And let's see what else we could do. Maybe we could do this one here. This is 6 comma negative 3. So this is all for f of x. Now for the inverse, these values are going to switch. So negative 3, 0 will become 0, negative 3. This will be negative 1, negative 2. This will be negative 2 comma 1. And finally negative 3 comma 6. All right? So now let's graph these. So x is 0, y is negative 3. X is negative 1, y is negative 2. X is negative 2, y is 1. X is negative 3, y is 6. Okay, and now we graph. There we go. All right. And if you can visualize a line y equals x drawn along this, you can see that if I flip the original, if I reflect the original around that blue line, I will get the red one. Okay? All right, last one. Here we go, same situation. Let's pick some representative points. So here I have 1 comma 0. And let's pick another one here. All right, so it looks like this is x equals 3, y equals 1.1 or so. We are going to estimate a little bit. X equals 6, y equals 1.8. So when we switch these, we get these corresponding coordinate points. Now, there's one other thing that switches, right? If x and y are switching, then the horizontals are becoming verticals, the domains are becoming ranges, and the asymptotes, right? If it's an x asymptote, it'll be if it's a horizontal, then it'll become a vertical asymptote, and vice versa. You notice here that the function has a vertical asymptote at x equals 0. Well, that will now become a horizontal an asymptote at y equals 0. Okay? Also, the domain of f of x is 0 to infinity, and the range is negative to positive infinity. Well, now the domain will be negative infinity to positive infinity, and the range will be 0 to infinity. All right, so let's graph these points. So when x is 0, y is 1. When x is 1.1, y is 3. When x is 1.8, y is 6. Okay, so it looks like this. And if the graph was riding along the asymptote in the negative values here, then it'll ride along the asymptote in the negative values here. And it'll look like that. Okay, so that's the graph of the inverse. All right, so that much for 1.7. Thank you.